So remind me to write on these boards. It seems that for many weeks I was still writing there and the camera was looking over there. So the videos from the previous lectures are only half useful. So I updated the seminar sheet with some things we already did so that we have a record of the group homological homology. And I'll also add what we did last week, the better proof of this first change of rings theorem. And I'll recall what that says because we'll use it today. Okay. So today we'll do more homological dimension. And the last theorem will be about these change of rings theorems for Noetherian local rings. So we'll have to say something about Noetherian local rings. And then we'll be saying a lot more about that in the lectures that follow. But next week, no Friday lecture or seminar. So we have a week off. It's not my fault that 100 years ago, a murderous gang of atheists took over Russia. So I'm not going to lecture on Friday. Right, so let me recall the first change of rings theorem. And look at the seminar sheet when I update it for an outline of a better proof than the one that we gave last time, which I took from Weibel. So it's the same proof, but there's a better way to organize it. Rather than doing induction, it's better to just consider the case projected dimension at most 1 or greater than 1. And in the first case, you use Tor. In the second case, you use Ext. So the theorem says the following. So let X in R be a central non-zero divisor in the ring. And if M is a non-zero module over the quotient, with finite projective dimension, over the quotient. Then its restriction to R also has finite projected dimension, and it just goes up by 1. just one bigger. And this is important for doing some kinds of inductive arguments. Okay, so that's the theorem. We gave a proof last time, but it was a bit awkward. Look at the seminar sheet when it's updated for a better proof. Okay, so today we're going to do some more change of rings theorems. So this one was about restriction. We could also do induction from one ring to another, in particular along the quotient. So the second change of rings theorem is same setting. So this is a central non-zero divisor. If we're working with commutative rings, then it's automatically central, but otherwise we need to assume this. And M a module on which x is a non-zero divisor. So multiplication of x on M is injective. Then I can take M and tensor it with R mod x, so induce it to an R mod x module, and ask what happens to the projective dimension. So I have the projective dimension of the original module, and I have the projective dimension of its of the induced module. So the induced module is just M mod x times M. And the claim is that the projective dimension can only go down. Well, it can't increase. Okay, so let's give the proof. I wish I could go a little further. So first, if the right-hand side is infinite, actually let me put the proof here. If the right-hand side is infinite, there's nothing to prove. So this is immediate. So suppose the right-hand side is finite. And let's observe let me make this a claim. Maybe I should have made this a separate lemma because we'll use this observation a lot. So pay attention. So under this hypothesis that x is a non-zero divisor in the ring and on the module, I claim that the tor of M against R mod x is 0 for I greater than 0. So in degree 0, it's just R mod x tensor M. That's M mod x mod M. But then there are higher tors, and all of those are 0. So indeed, apply this tensor with M on the resolution of R mod x. Okay, so that's one way to compute tor. I can resolve either variable, so I decide to resolve R mod x. So then what do I get? I get, let's see, M multiplication by x. I get M mod xm. And then I get the tors. And then the next tors vanish because they're against a free module. and so on. So I have this Tor. And the other Tors, the higher Tors vanish. So Tor I are this equals 0 for I greater than or equal to 2, just because there's no more stuff out there. And this one, so that actually would be true for any module M that I induce from R to R mod X. But now, to control the Tor 1, we use the hypothesis. Tor 1 is the kernel of this map. So it's the 0 divisors of X on M. This is M such that X times M equals 0. And that's 0 by hypothesis. OK? And now, let's take our M. We assume that it has finite projective dimensions. So let's take a short projective resolution. So now let M P0 P1 Pn let that be a projective resolution of minimal length. And tensor it with R mod X. So claim, if I tensor this with R mod X, I'll get a projective resolution of M mod XM. So if I apply R mod X tensor R to, let's give it a name, star, to this resolution, we get a projective resolution of M mod XM. So that's the claim. So let's check. We're going to do this kind of step by step. So let's first consider M P naught surjecting onto it, and then the kernel. So indeed. Let's consider, we'll call it K1 for kernel, P0, M, 0, and apply this. And then because of the vanishing of Tor of M, that will be exact. So by Tor vanishing for M, which was our previous observation, we get two things. We'll get that once I tensor with R mod X, I'll get an exact sequence, a short exact sequence. And also I'll get that the higher Tor of K1 vanishes. Because the higher Tor for P0 vanishes because it's projective. It's a summon of a free. And then the higher Tor of K1 becomes isomorphic to the higher Tor of M, which is 0. So we get a short exact sequence, M mod XM, P naught mod XP naught, K1 mod X K1, and higher Tor of K1 vanishes against R mod X. In particular, K1, X is a non-zero divisor on K1. And so now we're kind of in an inductive situation. Okay. And also note that each of these terms, P naught tensor R mod X, will be projective, because the projective always induces to a projective. We've observed that many times. So now, repeat this argument. On this projective resolution of K1. Okay. And note the terms after are immediately projective. Projective always induces to projective. Okay, so there you go. So it remains exact because the vanishing of this Tor. And so we produce a projective resolution of M mod X, which was no longer than the one we started with. Maybe it actually becomes exact further out, and we don't need those higher terms. That may happen. So the projective dimension could drop strictly. So for instance, if R mod X was a field, fields have homological dimension 0, so when I induce to a field, the projective dimension typically will strictly drop. Okay. So that's the second change of rings, and then there are some corollaries of this. So the first is, now I want to induce in a different way. Instead of quotienting out by x, I'm going to add in an x. I'm going to add in a free variable. So I'll start with the ring R, and then I'll form polynomial ring over R. Okay, so given, this is kind of notation, given a ring R, R mod R box X is polynomials with coefficients in R. And note X is central. Like when you form a polynomial ring over a non-commutative ring, X is by definition central. It commutes with the coefficients. So note a few things. X is a central non-zero divisor. It's a non-zero divisor because when I multiply, I raise the degree. And it's central by definition. So note X in the polynomial ring is central non-zero divisor. So the previous theorems are going to apply. That's one thing. And also note that R mod X, R adjoint X is free as an R module. It's the direct sum of R times, I can take the basis vectors to be powers of I. So this is free as an R module. Infinite rank, but free. Okay. Shoot. I kind of wanted to keep that. So here's the corollary. going to put a few things together. A little more notation. So given an R module, M over R, that's an R module, I'm going to use the same notation for inducing that to be an R adjoint X module. That's just notation for the induced module. Okay? So then the corollary is that if I take the projective dimension of the induced module I induce to the polynomial ring, nothing changes. And this innocent fact will be more important than it seems in a minute. So this will be part of allowing us to compute the homological dimension of polynomial rings. Okay, so proof. How do I want to say this? Yes. So note, I could apply second change of rings to this ring, where X is my central non-zero divisor. And so if I quotient by X, this will be R. And if I quotient M adjoint X by X times M adjoint X, I'll get back M. And now apply the second change of rings. So apply second change of rings theorem there. To this situation, R adjoint X and M adjoint X. So what does it say? It says that the projective dimension of M over R is no more than the projective dimension of the induced module. And so we're going to need the reverse inequality also. So on the other hand, we need the reverse inequality. So let's start with a projective resolution. Right, so hold on. So if projective dimension of M is infinite, we're done. Right? So if the left-hand side is infinite, we're done. In this inequality. If this is infinite, it forces that to be infinite, and then they're equal. So otherwise, choose a projective resolution of minimal length. Actually, it doesn't have to be minimal. We just want the reverse inequality. Yeah. So choose a projective, of minimal length. Choose a projective resolution of minimal length. This is over R. And now we're just going to tensor this with R adjoint X. Okay? That will give M of X here, P naught adjoint X, and so on. I claim that that's again a projective resolution. So certainly the terms will be projective because they're induced. We're using this fact over and over again. Induction of a projective module is projective. The interesting part is that the result will be exact. So claim this is star R adjoint X tensor R of star will be a projective resolution of M adjoint X. So we get the reverse inequality. And so indeed, the terms are obviously projective. Just because they're induced from projectives. And you could worry that once I tensor with something, it's no longer exact. However, the thing I'm tensoring with, I'm tensoring over R, and the thing I'm tensoring with is free over R. So there's no Tor. So tensoring with something free, more generally with something flat, is exact. So this functor is exact because R adjoint X over R is free. Okay? So there's the corollary. And now we can get the nice theorem. So far, when we computed homological dimensions, remember homological dimension was the supremum over projective dimensions of modules. That's the homological dimension of an algebra. And then we had some general theorem that said, well, you could also identify it with injective dimension. You could also just take projected dimensions of the ring modulo ideals and so on. There were various equivalent ways to say what the homological dimension was. And the only examples we had were things which were of infinite homological dimension. So we gave examples of group rings that were of infinite homological dimension. Or homological dimension 0, like a field or certain group rings of finite groups over fields in which the order of the group was invertible. And then we had things of homological dimension 1. So these were like the integers in a polynomial ring over a field in one variable. We didn't yet have things of homological dimension in between infinity and 1. Okay, so now we're going to give them. So theorem. So this is a kind of generalized Hilbert-Syzygy theorem. So I'll write Hilbert-Syzygy theorem separately as a corollary, but the proof is basically the same. Okay. Well, this proof is the same. So the theorem says the following. We're going to consider a polynomial ring in many variables over R. So the theorem is that the homological dimension of a polynomial ring in many variables, x1 through xn, is the homological dimension of the ring plus n. Okay, so each time you add a variable, you increase the homological dimension by exactly 1. Okay, so proof. And there'll be some simple explicit thing that I'm going to leave as an exercise for the seminar because it's fun. Okay, so by induction on n, it's enough to just consider adding on one variable. It's enough to consider the case of a single variable about which we already know something. We know that when we induce, nothing changes. And I'm going to give this a name. I'm going to call it S. Okay, so then by the first change of rings theorem, then x in S is a non-zero, central non-zero divisor so the first change of rings theorem, which I wrote at the beginning of the lecture but have now rubbed off, this says that the homological dimension of R plus 1 is bounded by a homological dimension of Rx. It actually says you have any ring, and then here, and then you have that ring modulo the central non-zero divisor, and you have this inequality. So we need the reverse. And so for this, I'm going to take a module over R of x. So consider, and I need to bound its projective dimension. So consider M over R mod x, of R adjoint x. And consider its restriction to R. So R maps to R adjoint x, just as the constant coefficient of a polynomial. And its restriction we'll call that M bar to R. So as an abelian group, it doesn't change. We're just forgetting the action of x and remembering just how the constant coefficient acts. Okay? So I have its restriction to R, and then I'm going to induce back. I'm going to adjoin a new variable. So then induce back. So consider S tensor R M bar. Okay? And I claim that this sits in a short exact sequence. So on the right-hand side, we'll have the thing we're trying to understand, M. And then we'll have this restriction followed by induction again. And I'll tell you what the differentials are, and then we'll check in the seminar that it's actually exact by constructing a null homotopy very explicitly. So the differentials are, here if I have a polynomial and an element of M, remember as an abelian group it's just M. So I still know how to multiply, and I can just send this to F times M. Here, if I have an element F tensor M, I'm going to send it to F times X tensor M minus F tensor X times M. And then if I compose, I multiply this on this and this on that, I get 0 when I take the difference. So it is a differential. And we'll construct a null homotopy on it to see that it's exact. So you check. So in seminar, construct a null homotopy to give exactness. It's always good to construct null homotopies, so we'll have practice with that. Okay? So now what? So note by this corollary, so by the corollary, the projective dimension of these restrict and then induce modules is the same as the projective dimension of those modules of the restriction. Projective dimension doesn't change under adding a variable. Okay, so that's good to know. Right. That was the corollary, or yeah, I guess I could say that's the corollary. And so then, now consider x. So now consider hom into this S blank n applied to this short exact sequence. This last short exact sequence that we just constructed. So we know that we can detect whatever the homological dimension of M, the projected dimension of M is, by finding some module for which the x into it is as big as possible. Right, that was one characterization of projective dimension. And if I look here, the projective dimensions of these two are the same. And so the maximum will appear like, say, xd here, and then I can get at most an xd plus 1 into n here. Okay, so we see that the projective dimension of M over R mod x is at most the projective dimensions of Rx here plus 1, which by this corollary is projective dimension of the restriction here. So this equals this plus 1. And this M bar, whatever it is, it's some R module. So that can be no bigger than the supremum of all modules over R of projective dimensions. So this is homological dimension of R plus 1. And so that's the reverse inequality. Any Rx module has projective dimension bounded by this. And so this must be less than or equal to this. This one? Okay. So this term here is what appears in this short exact sequence. Okay. So take over all modules n, hom into here and look at the long exact sequence in x. There will be some, say, maximum that appears here of non-zero x. And then beyond that, they will be 0. And so the maximum x that can be non-zero for this is at most 1 more than it appears for here in the long exact sequence. There'll be like xd plus 1 from m into n, and then 0, 0, 0. Okay. Right, so that's the proof. And let me state separately a special case. It's a very important special case. So this is the corollary. This is Hilbert's syzygy theorem. And I'll kind of rephrase it to say why it's called Syzygy's theorem. So if R equals K as a field, then that has homological dimension 0. So the theorem then says that the homological dimension of a polynomial ring over a field in n variables is exactly n. So any module over a polynomial ring has a projective resolution of length at most n, and if you remember how we characterized projective dimension, we said, in fact, if I took any projective resolution, suppose the projective dimension is n, and then I took any other projective resolution, possibly infinite, then if I go out to the nth term and take the syzygy, the kernel there, the result will be projective. So I can always truncate a possibly infinite projective resolution to a finite one of length n. Okay. So in any projective resolution of a module M over this polynomial ring, the kernel of this n minus first differential, so that's called the nth syzygy. Syzygy, I'll say where that word comes from in a second, is projective. And this is an important result. It's largely what makes computer algebra packages work when you deal with polynomials and many variables. It's some kind of finiteness result saying that if you have a bunch of polynomials, they generate an ideal, maybe there's some relations between them, and then some relations between the relations, and then relations between the relations between the relations, but eventually all of those many-fold relations will vanish. So some process will terminate. So this is what makes computer algebra work, theoretically. And the word syzygy has to do with these relations among relations. So the word comes from astronomy, and it means something like alignment of stars in the line of view. Okay, so that's the special case of this theorem. And now we're getting closer now to commutative algebra. So now we need to change gears a bit. So are there any questions about this general theory of homological dimension and what happens when you quotient by the central non-zero divisor? So what we're going to be doing now for the next few weeks, except next week when we don't have a lecture, is focusing on local rings. So I need to tell you some things about Noetherian local rings. I'll tell you a little bit today and more next time. Some of these things are easy to prove. We'll prove them in the seminar. Others are not so very easy to prove. So rather than giving a course on homological algebra, next time I'll give a short list of facts that we need to accept in order to make some progress. And then I can give you references for the proofs. They're not hard, but it would take at least a lecture to do all of that, and maybe 2. Okay, so definition. I'll just give the complete definitions. So now we're going to switch to commutative rings. And to distinguish them from the general case, I'm going to call a commutative ring A or B or C instead of R, S, and T, which were just general rings. So definition, a commutative ring with 1, so I always assume rings have unity, is Noetherian if every ideal is finitely generated. That's the definition. You can also do this for non-commutative rings, but then you have a difference between left ideals and right ideals. And so you have left Noetherian versus right Noetherian, and you could ask for it to be both, and that's stronger. We're just going to focus on commutative rings. And here's some facts, which are easy. One is that sometimes this is stated in a different way. So A is Noetherian is Noetherian if and only if every ascending chain of ideals, one ideal contained in another, stabilizes. So that's one fact that's easy to check. That's an equivalent way to say it. 2 is that this is also equivalent to every finitely generated module, every submodule of a finitely generated module is again finitely generated. This is also part of what makes computer algebra packages work. Every submodule of a finitely generated module is itself finitely generated. This is not true over a non-Noetherian ring. If I had an infinitely generated ideal, that would be a submodule of the ring itself. The ring itself is generated by 1. So for instance, if you took a polynomial ring and infinitely many variables, then the ideal generated by those infinitely many variables is not finitely generated. Okay, so easy facts. Second definition. Let me give examples. Principal ideal domains are Noetherian because all their ideals are generated by a single element. So I also have fields. Fields have no non-trivial ideals. There's nothing to check. So fields and principal ideal domains. So for instance, the integers or a polynomial ring over a field are Noetherian. And here's a theorem. Nutter Nutter's Basissatz. Basis is what she called, or what they called a generating set for an ideal, in Satz's theorem. A is Noetherian if and only if A adjoin X is. Okay? So once you have this, then polynomial rings and many variables over a field or over a PID are also Noetherian. This is Hilbert's? Hilbert's Basissatz? Actually, yeah, I think you're right. Maybe it's Hilbert's. Yeah. This is Hilbert's. It's the other basic theorem on normalization that's Nutter's. Okay. But I think that, so I think Hilbert proved this really just, what he really proved is that the polynomial ring and many variables, finitely many variables over a field, every ideal is finitely generated. And then Nutter realized that was a general fact about adjoining a single variable to something which already had this property. Okay, so there are very funny stories about Hilbert and Nutter. I shouldn't say them while being recorded, but you should go look them up. Hilbert had some wisecracks about this. Okay, so right, so in particular, a polynomial ring over the integers or over a field, these are Noetherian. Okay, so important facts. You do all of this in the maybe first day of a commutative algebra class. Or just in a general algebra book. It's probably, I'm not sure, it might be in Winberg's book, which is used here. But it's also in Artin's book on algebra, which is very nice. Artin's book on algebra, by the way, is a book about mathematics, not about algebra. I highly recommend it. Okay, so more definitions. So we're going to focus, in this case, on what's called a local ring. And in particular, we'll focus on the Noetherian local rings. So a Noetherian local ring, so A is a Noetherian local ring. So the definition for local ring makes sense in general, but in practice, we'll assume it's Noetherian. If there's a unique maximal ideal M in A, okay, and if there is such a thing, well, then there's the quotient A mod M, and the quotient of a commutative ring by a maximal ideal is always a field. So associated to a local ring, there's always a special field called the residue field. So then K equals A mod M is called the residue field. So let me give some examples. Fields are local. 0 is the maximal ideal, and the residue field is the field itself. So K, a field, is local with M equals 0 and K equals K. A little more interesting would be we could start with some ring which is not local, for instance, the integers. There are many maximal ideals in there. Those generated by the primes. And so what we could do is invert all the stuff outside the multiples of the prime. So there's a ring called Z sub round brackets P. I can write this as a subring of Q. It's A over B, where B, P does not divide B. Okay. So I claim this is a local ring. Maybe we'll check this in the seminar. This is local with M equals multiples of P, but inside this ring. So I can put stuff in the denominator as long as it's not divisible by P. And the residue field is just FP. Okay? So this is a typical example. Another example you could take, it's very similar, but you replace the integers with polynomial ring over a field. That's also a PID, so you can play a similar game. So I could look at K adjoint T. That's a PID. I could look at F, where F is irreducible. So the prime ideals in the polynomial ring are those generated by irreducible polynomials. So F is irreducible if and only if F here is prime. And then, so this will be inside the fraction field. So inside rational functions, it'll be P over Q, where Q is not in the ideal generated by F. Okay? And then this is also maximal, and M is what? It's generated by F. So P should be divisible by F. And the residue field is just the field you started with. Not true. Not true. Not true. The residue field is K of T mod F. So that's an extension of K, some finite extension of K. Unless K is algebraically closed, this will be a non-trivial extension when F has higher degree. Okay, so those are some examples. And then there are completions of these. So there's something called the p-adic integers that you maybe have seen. It's a completion of this. You could also look at power series in T. That's a local ring where it's a completion where you take F equals T, and so on. So there are lots of examples. These are low-dimensional examples. They're higher-dimensional examples. And what do we have? We have 20 minutes, 18 minutes? OK. So I need to give kind of the most important fact about Noetherian local rings, which is something called the Nakayama lemma. This is, in commutative algebra, probably the most important lemma. And often lemmas are more important than theorems. This is the big one. It's really easy to prove, but very, very useful. So Nakayama lemma says the following. And there'll be a bunch of corollaries of it. And we'll prove it in the seminar. So the Nakayama lemma says, let A be a Noetherian local ring. Sometimes people, just to make all the notation clear, they write a local ring like this. The name of the ring, the name of the maximal ideal, the name of the residue field. So this is a Noetherian local ring. The Noetherian part is important. We're going to want submodules of finitely generated modules to be, again, finitely generated. And M I think it should probably be non-zero. Let this be some non-zero. No, it doesn't need to be non-zero. M is just a finitely generated module. Then the following are equivalent. So I have a map from A to A mod M. So I can induce along that. And K is a field, so when I induce, I'll get a vector space over that field. And it will again be finitely generated. It'll be a finite dimensional vector space. So it says that, let's see. The submodule of the form elements of the maximal ideal times M, that's always a submodule of M. Suppose it's equal to M. Well, that's obviously equivalent to M mod maximal ideal times M being 0. Okay. And that's obviously equivalent to, how do I compute that? That's the same as tensoring with the residue field. Okay, so that's just a different way to write the same thing. And the content of the lemma, so those three are obviously just equivalent. The content of the lemma is that D, this is the same as actually M itself being 0. So M is 0 if and only if, when you tensor with K, it's 0. So we can detect the 0 module just by tensoring with K, and that's good because K is a field, and so we're reducing ourselves to dealing with finite dimensional vector spaces over fields, and those are easy to deal with. And to prove this, let me tell you the one important fact. And then we can prove it in the seminar. So important fact, I should have told it to you right after I gave the definition. So you can check that if A is a local ring, the units of A, so the invertible elements of A, invertible with respect to multiplication, the units of A are precisely of the form one plus x, where x is in the maximal ideal. Okay, so this is easy to check. So that will get used in the proof of Nakayama's lemma. And then the main corollaries that we'll need of this. The first is that suppose A, Noetherian local, M over A finitely generated, so Nakayama lemma applies. We often want to find generators for M. We'd like to be able to test that a set of elements forms a generating set. And in fact, we'd like to check that it forms a minimal generating set. So then, a set of elements in M generate M if and only if the reduction modulo the maximal ideal let me call this M bar, generate. And it's a minimal generating set in the sense no subset also generates. If and only if these form a basis. The images form a basis. Okay, so this is very important fact. And related fact, once you know this, you can prove that, again, A Noetherian local, M over A finitely generated. Then M is free. How do I want to say this? M is projective. If and only if it's free. So there are no funny projective modules over Noetherian local rings that are finitely generated. There's only the free ones. They're not some non-trivial summons of free ones. Okay. Very good. And what else? Do I need anything else? One more thing. Sorry, I am giving you a bunch of facts. We'll prove a bunch of them in the seminar, but I want them recorded because we're going to be using them a lot. So any questions so far? Say it again. The ring is Noetherian and it's local. Yeah. So you can talk about local rings that are not Noetherian, but all the theorems we will prove will assume both Noetherian and local. Non-Noetherian rings are important, but they're much harder. And the only place I typically encounter them is in kind of some fancy parts of number theory. Okay. All of the rings that you first encounter in number theory when you're starting out are Noetherian. So things of like rings of integers in a number field. And okay, right. So here's the one more thing we need, is the notion of a minimal resolution. This is something special about local rings or graded rings. You can also study graded rings over a field, and then the kind of constant part corresponds to the residue field, and then the theory behaves a lot like that of local rings. So let's say definition. Let M be, I guess the definition makes sense, but it's probably less useful. So let M be a finitely generated module over a Noetherian local ring. Then a minimal resolution a minimal free resolution is a resolution, a free resolution, so there are differentials like this. Maybe it goes on forever, where the terms are free. If they were just projective and finitely generated, they would automatically be free. So where the terms fi is finitely generated and free. Okay. And what makes it minimal? If I reduce it modulo the maximal ideal, the differentials become 0. So d I is 0. This is mod the maximal ideal. So if I tensor this differential with k over a, it becomes 0. Okay, and the basic fact is that minimal free resolutions exist, and they're unique up to isomorphism. This is something very special about working with resolutions over a local ring. So, lemma. Minimal free resolutions exist for finitely generated modules over Noetherian local rings. And are unique up to isomorphism. Moreover, in particular, the ranks of the FIs are determined. Moreover, and you can compute them. So moreover, rank of the free module Fi is equal to dimension over the field K of the vector space Tor I with the residue field. Okay, so this will follow from this fact about minimal set of generators being a basis. Okay, how much time do we have? 2-3 minutes? So maybe we'll do the details in the seminar, but maybe I can at least indicate why this works. So the idea of the proof, and this will maybe show us how to use all of these facts that I've written. So the idea of the proof is choose a minimal set of generators of M. So the construction is inductive. Okay. So let me call this N naught, because I'm constructing the 0th term of the resolution. So then we get a surjection from F0, which is N naught copies of A, onto M. I just send the basis vectors to the generators. So that's a surjection. Okay. And there's a kernel. Call it K1. And now because A is Noetherian, this is important, K1 is a submodule of a finitely generated module, therefore it's finitely generated. So since K1, since A is Noetherian, K1, K1 is finitely generated, so can choose minimal set of generators for K1. Let's call them M1 up to Mn1 in K1, and consider F1, which is rank N1, surjecting onto K1, and then there's a kernel K2, and then you repeat. Okay, so now this includes into F0, so the differential is F1 surjects onto K1 and then includes into F0. Okay, so you continue like this, possibly forever. But at each stage, you're doing something finite. And you can check, because of that we chose everything to be minimal, that when you tensor this with the residue field, the differential will vanish. So that this we can check in the seminar. And then from that, you'll see that you get this equality. Okay, so that's the idea of the proof. Let's stop there.